thank you for coming. My name is Minli, and I'm a postdoc here. Today I'm going to present my work here on fault detection for data centers. And we mostly use our technique called paraversor to detect permanent faults, and we leveraged heterogeneous parallelism in the system to make it more affordable. So first, let me talk about the problem in fault detection in data centers. Well, commercial data centers will use software scanner techniques to detect permanent faults. This would involve either taking a machine out of production for some lengthy period of time to run tests, and it cannot happen often, or it can be smaller tests that can run in production alongside server workload. However, these smaller tests also mean that it covers a smaller amount of permanent faults. Meta and Google have reported that current servers would frequently suffer from faults that do not crash the system, so they are just staying silent. And even with current techniques, it can take up to 6 months to actually detect them and decommission faulty hardware. This means that during that long window of time, this machine is just generating wrong data, wrong results, and we have no idea about it. So how about we look at how some safety critical systems would work on detecting these errors? Well, for example, for automobile systems, you will usually use like dual core lockstep systems. This involves duplicating the workload and running them on identical cores that are tightly coupled. And any error will be detected because these cores would not generate the same result. However, this would also double the area and as well as the power needed to run the same workload, which is not acceptable in a data center scenario where error detection is not always needed. This is why we look at the heterogeneous parallel error detection, where instead of having two identical cores, we would have one large core that we call the main core that will run the workload efficiently and fast. And we will have a large number of dedicated smaller cores that we call checker cores to run the duplication of the execution to check for errors. These checker cores will not access the memory system, instead access what we call load store log, and this is being filled in by the main core execution. While these little cores are individually very energy efficient and hence slower, together in parallel they will match up with the main core performance. The problem, however, is that even though these are little, a lot of them together still take up like 25% overhead in area, which is still not acceptable for data center scenarios. And that's why we come up with our solution paraversor, which uses the existing heterogeneous cores in the system instead of adding new dedicated cores. So in this system, both the big and the little cores can run the server workload without any problem. And we can also configure some of the cores to be checker cores. To check for the data, to check for any error, we will first split the workload on the main core into multiple segments through checkpointing. And we can replay each segment onto a little core for duplicate execution. While these cores will execute the segments slower, multiple of them in parallel will make it keep up with the main core performance. However, the problem is in a server scenario, you sometimes do not want that much resource spent on just checking. You still want to be performing your workload. And how do we solve that problem in cases where there is not enough resources for checking? Well, if the workload on the main core is more critical, that you want to make sure that there's no error in it, then you will have to delay the progression of the main workload. And this is what we call the full coverage mode. And on the other hand, if the performance of the workload is more important, then we will just simply do our best and some segments will just not be checked. This is what we call the opportunistic mode. So overall, our paraversor scheme is a system that we can dynamically toggle between having more performance out of your overall server, or we can have a higher error detection capability. To make this happen, we need to add some structures to the core. And here I show a general, like a simplified diagram of a general purpose core. So to this, we will add a register checkpointing unit and a timer. These structures are here to split the workload into different segments and take checkpoints. We will also add a load store push unit to push data from the main core to the checker core. And we extend the L1 data cache to be able to store load store log cache on the checker core. And we also add a load store comparator to compare for differences in data. All of these structures together will add only about a 1 kilobyte of storage overhead, which is negligible compared to the 25% error overhead of dedicated checker cores. Next, I will show how these structures actually work. So on the main core side, we have the L1 data cache just as a traditional cache, and we're not going to use the load store comparator. At the beginning of the segment, we first take a register checkpoint in the beginning. We send this through the load store push unit over the network and onto the checker core's register checkpointing unit. This is so that the checker core can start execution at the exact same point as the main core. And then we start counting the number of committed instructions in the segment. This is so that the checker core can stop at the same time. And then during this time, any load store memory accesses will also be duplicated with this information sent again into the checker core being stored in the load store log cache. And then finally, at the end of the checkpoint, at the end of a segment, we take another checkpoint. We take the number of committed instructions, and then we send these all over again to the checker core. On the checker core side, we are not going to use the load store push unit, but we are going to configure the data cache to be load store log cache, and also use the load store comparator. Here we first restore from the checkpoint so that we can start execution at the same point as the main core, start counting exactly the same way. And then instead of asking the data cache for anything on memory accesses, we will send requests to the load store log cache, which will forward information onto the load store comparator, where memory access address or store value will be compared and checked if there's any error. Then when the timer indicates us that we are at the end of the segment, we will compare the register values against the end of segment register checkpoint that we had to detect any errors on those values. We evaluate our system on, with Gen 5 architecture simulator. We model our big cores based on ARM Cortex-X2 cores, little cores based on ARM Cortex-A510 cores. The big core is used both as main and checker core, and for more energy efficient configuration, we use 2 checker cores at half the frequency and lowered voltage. We use 4 little cores to keep up with the main core performance, and also lowered frequency and voltage for different energy efficiency points. And finally, we use even less little cores and even at lower frequency to showcase how well we can detect errors with opportunistic mode, even with little resources. First, I will show the results on our full coverage error detection. So compared to a baseline where there's only a main core running the workload, adding the big cores for checking only adds about 1% slowdown. Little cores adds about a bit more slowdown, and naturally less frequency shows more slowdown. But on the energy side, that's where we get more affordable. So with an identical core, there's about 87% energy overhead. This is high, and this is comparable to a dual core lockstep system. What's interesting with the heterogeneous mode is that with these different more energy efficient configurations, we can get that overhead down to half or even more. And if we find the minimum energy delay square product configuration per benchmark, we can get down to only a third of the dual core lockstep energy overhead, the same full error detection coverage with only 4.2% slowdown. On the opportunistic mode side, we can get the overhead down to less than 1%, regardless of the configuration. And we inject errors into the spec benchmarks to see how well we can detect them. With only 1 little core at a quarter of the frequency, only 2 benchmarks couldn't detect all injected errors. At 1 little core, half the frequency, only 1 benchmark remains, cannot detect all the errors. And all errors are detected with 2 little cores at the full frequency. In conclusion, I just presented our work that aims to solve fault detection in data centers where silent data corruption can stay undetected for a long time. So our solution parameters can be configured, can be dynamically configured between having more performance or more error detection capability. We get efficient opportunistic mode with spare resources with a higher detection coverage at less than 1% slowdown. And we can do full coverage with only about a third of the energy overhead of a dual-core lockstep system with only 4.2% slowdown. And that concludes my talk. Thank you very much.